Thank you, Daniel, and thank you for coming. I will try to, in my talk, try to convince you that life has been present on Earth throughout the whole geologic record, and probably that life already in the beginning of the geologic record, which reached about 3.8, 3.9 billion years back in time, that life already at that time was relatively advanced and had acquired the ability to perform some kind of photosynthesis. And also that through this ability to perform photosynthesis, life has deeply influenced the planet, and therefore we cannot, through the geologic record, get any insight into the prebiotic world and what conditions life arose under. But just to get us into some kind of context in time, I think it's instructional to look at how long the geologic record really is. And if you see here, this is a graph that shows all time. Time was invented here during Big Bang, 13.7 billion years ago. And actually, the geologic record covers almost 1/3 of the entire amount of time that existed in the universe. So you would think that we could learn something from this. And as Danielle has already explained, we cannot learn as much as we would like, but we can definitely learn something. So I'll jump right into some of the observations we can make if we go back to the earliest part of Earth record, which starts in West Greenland, a place called Isua, where we have rocks that are laid down on the surface of Earth and have been preserved relatively well until the present. What you see here are pillow lava structures which form when volcanoes have eruption underwater. And I think it tells us, for one thing, that water was present, liquid water. We had oceans already 3.8 billion years ago. And of course, it tells us that we have basalt volcanism. This is not too surprising, because that is kind of the generic feature of all rocky planets and even asteroids, that they have basalt volcanism. But this tells us that probably the ocean was somehow in contact with basalt to a large extent. I think another interesting feature that we can read from this figure is that Earth is not as dynamic as many of us like to claim. You know, we always claim that the Earth is such a very dynamic planet, but this pillow lava pillow formed during maybe 30 seconds, and this one formed 30 seconds later during 30 seconds, and they're still there. So Earth is not all that dynamic after all. Another feature we find in these oldest sediments, and what we find throughout the Archean, is banded iron formation, which is the kind of rock like this, where you can see alternating layers of mixed valence iron oxide minerals, that is magnetite and quartz. You can see from this picture that the rocks are deformed, they have been metamorphosed and everything else, but we can still recognize that this is a sedimentary rock formed in water, and I think everybody believed that it formed by precipitation of these minerals out of a solution. So again, it tells us something about the surface conditions. Water was present. We had some kind of geochemical cycles in the water where we could transport iron, which basically gave us information that the early atmosphere was devoid of oxygen, was oxygen-free, which made divalent iron soluble in the ocean. Among these rocks, we have a very few preserved windows back into the ocean floor at that time, where we can really see sedimentary structures like we see here. You have a gray layer, which is a mud flow deposit, some kind of a mud avalanche fell down a submarine slope and settled during a very short period of time. But between these mud flow units, we also have black shales, which form very, very slowly by the very slow settling of clay onto the ocean floor. So these rocks are really interesting because they give us a very good time section, or would you say a good idea of the everyday conditions on the planet. They are not related to any catastrophic events. They are just the background sedimentation in the ocean. And features like this form maybe during 100,000 to 1 million years. So it gives us also an idea about the stability of the system we are dealing with. And it basically tells us that environmental conditions were stable over a very long period of time in this ocean. If we look a little bit closer at the sediments, we can see here's a petrographic thin section about 0.5 centimeter across. And what you see in this thin section is that we have extremely well-preserved, very, very fine lamination in these sedimentary rocks still until today. And obviously, also, we can see that there are some black layers and some white layers. The colorless layers are formed of feldspar, quartz, biotite, ilmenite, things like that. And can best be explained as ashfall on the ocean floor, on the ocean surface that's settled rapidly to the ocean floor. So these are volcanic ash layers, whereas these layers are quartz and white mica, which is basically the equivalent of clay. So this is a very slow sedimenting clay on the ocean floor. And as you can tell, of course, quartz and white mica is not black, so there must be something else that makes these rocks black. And that something else are these tiny little particles, about 2 microns each, which are made of graphite, just pure elemental carbon. So I think that is a very interesting observation that in the open ocean, when we had slow sedimentation, we had a co-precipitation or co-sedimentation of reduced carbon down to the ocean floor. And the ambient condition on Earth would be that carbon is tied up with oxygen in carbonate or CO2 or bicarbonate or something like that. And at least on the present understanding of the Earth, the most efficient way of producing large amounts of reduced carbon is by biologic activity. But we can also, of course, probe a little bit deeper into the origin of this carbon by looking at the isotopic composition. And it turns out that the carbon in these layers has a composition of about -26 per mil delta-13C depletion relative to a normal carbonate standard. So the carbon in these sediments has all the characteristics of biogenic carbon today. And I think we know of no other process that can produce carbon in the open oceans that has this isotopic signature other than life. And also, I would like to stress that this is not finding a random piece of carbon somewhere that we don't know how to derive. This is carbon found in a sedimentary context, in a environmental context, where basically the only model that really fits would be that it's biogenic, which is supported by the isotopic signal here. You might think that this graph is not the most elaborate PowerPoint slide you've seen in your life, and that is true, but that stems from the fact that it was written with a rock from Israel, just to identify to you that these rocks do not have trace carbon. They actually have carbon as a major component. So it would suggest that there was a high content of carbon in these rocks. And if we accept that this carbon was biogenic, that would mean that if you have a high amount of carbon in the rock, there would have been a high productivity in the ocean. And we can rule out that the high carbon content is due to a slow sedimentation rate, because together with Chris Kripal, who is also, hi Chris, coming on stage later, we have tested for cosmogenic components in these sediments, and there is a very low concentration of cosmogenic components, which basically means that it was a, say, normal sedimentation rate in this basin. So if we have high productivity of biogenic carbon in the ocean, that basically would suggest that the life that existed in the ocean at that time was not the first life on Earth, because first life would, as we understand it now, would live off chemical energy sources, which are not abundant in the open oceans, but also the fact that we have this high productivity would basically require that we have some additional energy source relative to just chemical energy sources. And that additional energy source, the only one we know, of course, is sunlight. So this would suggest that some kind of photosynthetic strategy was acquired by these organisms already 3.7 billion years ago, which is the minimum age we can give these rocks. So I think that we can suggest that life had existed on Earth a long time before 3.7 billion years ago, because it had already evolved photosynthetic strategies at that time. Another interesting feature we can observe in these shales is that they are enriched in uranium, but not in thorium. And the uranium enrichment is something we also see in modern black shales, and that originates from the fact that during slightly oxidized conditions, uranium is soluble in ocean water as uranyl. Normally, uranium and thorium are geochemical twins in many geologic environments, and they travel together, so to speak. The only way you can fractionate one from the other is basically by having slightly oxidized water in which you can dissolve the uranium but not the thorium. And what you see is that the uranium has been transported on the scale of an ocean basin and then co-precipitated with the reduced carbon and settled into the ocean sediments. And what when we have done this study, we find that only these shales have this uranium enrichment, and we can check that the uranium enrichment was contemporaneous with the sedimentation because of the lead isotopes that are derived from decay of the uranium. Basically, take us right back to 3.7 billion years ago. So these rocks have lived in an ocean where we had some kind of redox contrast, which is also expressed, of course, in the banded iron formation, which also require that you dissolve iron into more reduced water and precipitate it out of more oxidized ore by some kind of biologic activity directly. So if we accept that we had a biosphere already 3.7 billion years ago, or 2.8, or whatever age really is, we accept that some kind of photosynthetic strategy was already involved. What does that matter to a person like myself, who's a geologist? Why would I care about that? Well, the reason why I care about that actually goes back to the photo of the pillow lavas we saw at some point. Because as the pillow lavas really indicate, Earth is not a very dynamic, it's actually a very boring planet. Very little happens. And the reason why very little happens on Earth is that the energy conversion in the inner part of Earth that drives the plate tectonics, the folding of the mountains, the volcanoes, earthquakes, everything else, is only about 87 milliwatts per square meter today. It was sometimes a few times higher during the Archean, but still it's a very, very small number of watts that are driving the geologic engine here. In comparison, of course, we have 340 watts per square meter coming from the sun. But because the visible light has very little energy relative to the bond strength of most surface materials, it doesn't actually deliver much chemical-free energy, this 340 watts. It drives the climate and the weather and the atmospheric circulation, ocean circulation, whatever, but it doesn't do very much in terms of chemical-free energy. A situation that life was unhappy about and therefore invented photosynthesis that could convert photon energy into chemical-free energy. And that was such a successful strategy that after the invention of photosynthesis, basically the chemical-free energy production by photosynthesis is completely outcompeting the energy conversion in Earth itself. So today, life is the strongest geochemical force on the planet, and it is 3 times stronger or 4 times stronger than Earth itself. So that's the reason why it is so important that photosynthesis arrived early on the planet and could basically control the geochemical cycles. If we take a look back again on these banded iron formations and start wondering, okay, they can tell us something about features on the early Earth, and they cannot tell us everything. But one thing, as we have already learned, is that they tell us that the surface environment was largely anoxic, or maybe totally anoxic. So we had the solubility of iron in the ocean water. But maybe they can tell us something more, and what more they can tell us is that actually they can address the question about the CO2 content in the atmosphere. That's something that's been discussed over a very long time, and we have had a long period of time where there was near consensus that the early Earth atmosphere was extremely rich in CO2. There's Jim Casting's suggestion derived from a solution of the faint young sun paradox, basically that to compensate for the fainter sun during the early part of Earth history, you could that could have been basically compensated by having a high CO2 content in the atmosphere. Which is a quite good idea. The only problem is that there is no geochemical evidence to support that. There's no direct indicators of very high CO2 content in the atmosphere. And CO2 is reactive with many minerals, and we don't see that in the geologic record. If we assume that the banded iron formations formed in the ocean and in contact with ocean water, and ocean, of course, is in contact with the atmosphere, we can try to put some limits on the CO2 content of the early atmosphere. And what we get is that the presence of magnetite rather than siderite would bring us somewhere along this boundary line in the phase diagram. We cannot measure the oxidation state of the atmosphere directly, but if we use hydrogen as a proxy for that, and we say, okay, this is the ambient conditions on Earth, that is basically the conditions determined by the presence of basalt, and we know that these reactions produce hydrogen, but we also have microbes that might consume hydrogen, for instance, methanogens that we believe existed, at least during part of the Archean. They could basically have grazed hydrogen down to this level, and that would bring us into this box of conditions for the CO2 content of the atmosphere, which is basically very close to present day, maybe 4 times more than present day CO2, but nothing really dramatic. So I think this does not tell us that the prebiotic world was at a low CO2, but basically already 3.8 billion years ago, life had such a strong control on these factors that it had been able to maintain CO2 at this level ever since. This is, of course, a very limited insight we have into the atmosphere at that time, and there's a number of first-order parameters that we have absolutely no idea about. We don't know anything about nitrogen because it's inert and we can't tell anything about it. We don't even know the total pressure of the atmosphere at that time. So I think that we cannot constrain the environment 3.7 or 3.8 billion years ago, but we can at least constrain a few parameters, which I think is still much better than nothing. The free energy production by photosynthesis is basically used to keep the atmosphere and ocean out of chemical equilibrium with the substrate. On a lifeless planet, you would have an ocean that would, shortly after formation, would attain approach chemical equilibrium with the basalt floor underneath it. But what happens if you have photosynthesis is that these 300 milliwatts are going into keeping the ocean and atmosphere out of chemical equilibrium with the basalt, which basically results in the process called weathering and basalt alteration. And the consequences of that is basically that you form new minerals when you have basalt in contact with ocean water. And these new mineral assemblages during secondary heating, during plate tectonic processes, give rise to, as you see here, this was a vesicle we saw before that has been filled with secondary minerals, and here is a vesicle band in a metabasalt that has been subjected to high temperature. And what happens is that you start to sweat out new types of materials out of the basalt protolith and form the rock type called granite, which you see here. And one can sketch out a series of geochemical processes that are dependent on the activity of weathering, which is, again, forced by life, which leads from a basalt world to a world that also has granite on the surface. I think many of us think of granite as the most common rock we can see, the most common rock on Earth, but in reality, granite is an extremely rare rock. It only covers about 1/3 of the surface of our planet till now, and the 2/3 left are still covered by basalt. It's only about maybe 20-30 kilometers thick film of basalt relative to the 6,300 kilometers into the core of the Earth. So granite is really a very, very thin film that is covering a very, very small part of Earth's surface, and which has been growing since Archean time and until now. It's a process that started about 4 billion years ago, and before that time, the continents were non-existing as far as one can tell. There's still controversial, but from the geochemical modeling of mantle, of the components of granite that have been extracted from the mantle, it would suggest that the continents didn't exist before about 4 billion years ago. So, and also, we don't see granite on any other planet that we have seen anywhere. So, I think that the continental crust on Earth is a biosignature, basically. It's something that is formed through the interaction of life with the environment, and again, it has obstructed our view because the continents have been in existence since 3.8 billion years ago to some extent, and again testify that the impact of life had been massive since that time. The living organisms not only act, of course, on the ocean and the basalt floor, but living organisms also emit gases. As you can see, this famous Frenchman who was famous for farting the Marseillaise. But it basically means that the living organisms deeply impact their environment. And on Earth, this has led to not only a change in the chemical environment, but also on the radiative properties of the planet itself. Here's a photo from the high Arctic where we have thin, high clouds that are very dissimilar from the ones we see over Montpellier today. And I think the current insight is that the cloud types that we have on the planet today are strongly influenced by these sulfuric gases that are emitted by eukaryotic organisms and oxidized to sulfate in an oxygenic atmosphere. So if you go back to the early Earth, not only were or we can say that the atmosphere would have been different from now, but also the radiative properties of the atmosphere would have been different. And that can actually help us explain why we do not need the high CO2 to maintain clement conditions on Earth, despite the faintness of the sun. This is a rather busy diagram. I apologize for that, but I just say that we can model the surface temperature of Earth if we assume that the surface had no continents. Basically, the surface was darker than it is today, and that the clouds were different due to the absence of the sulfuric gas emissions from eukaryotic organisms. And that together would give us a lower planetary albedo, and even with the fainter sun, we would be at positive surface temperatures during the Archean due to those different properties of the surface of the planet. And I think if we piece all this together, it seems as though the Earth has been, since 3.8 billion years ago, has been in the grip of life, and that various feedback mechanisms have basically maintained the surface conditions on Earth within a relatively narrow band of temperatures and other parameters, despite the enormous changes in the conditions surrounding the planet, for example, the lower luminosity of the sun. So if we look at the planet in a drawn-to-scale graph like this, you can see that actually you can't see anything. The surface film, which is relevant to us, is completely invisible here. You can't see the atmosphere and you can't see the lithosphere. So the Earth is 1,300 degrees here underneath the lithosphere and minus 200 and something out here. And in that very, very, very thin film that is separating these two extremes is that's where life plays out, and that is where life is basically converting so much energy that it is outpowering everything that's going on inside this big sphere. And the products of the life activity on the surface are then communicated throughout the whole system by plate tectonics. Here you can see the outline of South America in this seismic tomography, and you can see the Pacific plate basically plunging all the way down to the core mantle boundary, bringing the products of the surface alteration and the surface processes by life all the way into the core mantle boundary. So our entire planet is completely and utterly influenced by life down to the core, and has been so since about probably 4 billion years ago. Include that geologic record does not allow us any insight into the prebiotic world, but it tells us that everything we can study through the geologic record is to some extent influenced by life, and that life must have emerged on Earth very, very early to basically have a total control of the planet already by 3.8 billion years ago. So, thank you.